Good afternoon, everyone. It's so great to be back at Simons. I'm Jiantao. Today I'm going to be talking about some recent work we did with both colleagues at Berkeley and also Nvidia. So it's called From Beats to Rounds. From the name, you can tell that there will be some information theory going on. We would like to talk about new decoding strategies for diffusion language models, which recently are actually very hot. There has been a new startup raised 50 million. Google also released the Gemini diffusion based on joint work with my students Hongyu Fu and Baihe Huang from Berkeley, and also my colleagues at Nvidia. So the background, we focus on the language modeling problem, which has been the core innovation of recent generative AI revolution. Idea is that you have a sequence X, denoted as X1, X2, Xn. Each one is called a token. I would like to model the joint distribution. And the traditional large language model is modeled in the autoregressive manner, which basically says that I would like to factorize the joint distribution as a summation of log conditionals, and I would like to minimize this log loss. So basically, idea is that given the history, x1, x2, xi minus 1, I would like to make sure the model can predict the real xi as accurately as possible. So that's so-called the next token prediction paradigm that is underlying ChatGPT, Gemini, and the Claude. There's a new paradigm called the mask diffusion model, also called discrete diffusion model. Idea is slightly different. It's basically saying that the one limitation of the autoregressive model I do not really like is that it forces me to decode from left to right, which basically says when you are interacting with ChatGPT, then you have to decode one by one. This one is saying that what about I give the model a harder task, which is saying that, say, here I'm writing the whole joint distribution as expression over sigma, where sigma is follows the uniform distribution over all the permutations on the sequence of length n. So basically, this one says that ideally, suppose you give me the values of these tokens at some arbitrary location, sigma 1, sigma 2, and sigma I minus 1. You are really supposed to predict what will be the token at the location sigma I very well. And since I'm taking this expectation, I'm actually forcing the model to learn how to conduct decoding for any location based on tokens revealed to the model at arbitrary locations. So you never need to do it from left to right. Basically, I can give you lots of tokens maybe on the right or randomly scattered. I pinpoint another token, you are supposed to decode this. So the loss function you use in training the models is also very simple. By Jensen's inequality, you can actually lower bound this joint probability assumption by this one. And this one looks so similar to the autoregressive one. The only difference would be that I've added another expectation. So in reality, how do you really train this? In autoregressive model training, you basically ask model sequentially to predict the next token again and again. Here, what will happen is that I randomly would mask certain tokens, and I tell you, here's another location, please help predict what's going to be the output.
So is there any assumption on the x sub i's?
That's a very good point. So the whole point of large language model is that I would like to come up with a particular architecture, which is captured by this PMDM. There's a parameter there. Now, in training, I hope that this parameter would be learned by minimizing this loss function to really capture the real underlying distribution of your data.
So there's an assumption that there exists an underlying distribution, for example.
There exists one, and you hope that your modeling of the PMDM or the autoregressive one is good enough. So it really accurately approximates the distribution.
Are you assuming the xi's are independent or not?
Absolutely not.
Okay.
So each xi is very similar to the words you observe when you are using ChatGPT. Then they can model extremely complicated distributions.
Okay.
No stationary assumption, nothing like that.
Absolutely no. Okay, so basically, mask diffusion models, you can think of this as one approach of modeling the marginal condition distributions given the revealed tokens. So here, suppose I reveal the tokens at location A to you. Then if you look at the output of this PMDM, It's actually trying to model what's the conditional distribution of that particular token, conditional all the tokens revealed to you at arbitrary locations. So this one does give you the possibility of conducting parallel decoding. Because suppose you have another 2 tokens x and xj, they are not in the set A, but they are conditionally independent given xa. Then you are able to sample this at the same time. So you're able to essentially increase the sampling efficiency of your algorithm.
But I just thought you're starting out assuming you don't know anything. So how would you know they were independent?
That's a very good point. Turns out one can evaluate the quality of the generations to infer whether the assumptions were actually right. So that's a holy grail of modeling human language or any arbitrary data. So the only way to really test this would be using the system, just like we are impressed by ChatGPT. So why parallel decoding matters? In the traditional GPT style, you ask a question, say you want GPT to write code for you, write down the factorial function. GPT will generate tokens one by one for you, and it could be slow. In parallel generation, what happens is that if you use Gemini diffusion these days, you send in a prompt, initially all the tokens will be masks. And then you see that there will be some random actions, certain masks will be flipped, they will show you some tokens, and then you'll be able to observe the final decoded sequence very soon. So the number of rounds would be generally so much smaller than the total number of tokens in the sequence. Potentially can be fast inference, better for structured tasks such as code generation. I'm going to generate a huge amount of codes, and this one will actually be faster. I'm going to talk a little bit about what's the current approach people actually take to decode this. The most prevalent approach is called confidence-based decoding. Idea is the following. So basically, say you have already decoded certain tokens xa. Then you look at all the other locations xi where I is not in A. Then you look at the probability it assigns to each to different tokens. Then you pick the token with the highest probability at location I and denote this as a confidence at this location. Basically, if that one is very big, it means that the model is very confident at that location. Then that token needs to be decoded. There are quite a few different approaches to employ here in order to utilize the confidence. For example, you can say that to decode once, I just need to look at all the tokens with confidence above certain thresholds. There's another method, so-called dynamic threshold, which is actually proposed in the FastDM paper. The idea is saying that where I'm decoding many tokens all at once, suppose the confidence satisfies this inequality, which actually means that C is pretty close to 1 when M is large. Then basically I can decode all M tokens all at once. Idea is that you condition XA, you sort all the other tokens of confidence from largest to smallest, then you can actually decode all the M of them at the same time. So the reason why this is an interesting assumption, because you can actually show in theory, if you decode tokens following this idea, then only looking at the marginal distribution, you'll be decoding exactly the same tokens you would have decoded if you actually knew their joint distribution. So that's what the theory guarantees. So I want to give you one example, maybe we're running out of time, showing that how parallel decoding works. So here is based on confidence decoding. Generally, confidence is being updated once we are decoding the whole sequence. Basically, you see that still kind of operates in a sequential manner. So you go from left to right, but it's not exactly like a one by one. So here's also a plot I want to show. Basically, since you are actually adjusting the confidence of each decoding step, if the confidence you assign for each decoding step is very high, which means that you need to decode very few tokens due to this assumption, then turns out the accuracy is high because y-axis is accuracy, x-axis is the average number of steps. So, but suppose you decrease the confidence requirements. You say that even if the token is not very confident, I can still decode that. You can significantly reduce the number of steps, but you also see your accuracy would actually drop in important benchmarks. So that's actually one very big issue currently people face in increasing efficiency in decoding, because once we are able to increase the efficiency, we see the accuracy really drops. And the whole idea is really to push this Pareto frontier. then when we actually initially studied this problem, we realized that there's very interesting information theory behind this. So at least I want to convey this point. So the confidence-based decoding sounds very nice, but as a theorist, the first question we ask is that really able to reduce the number of decoding rounds? Intuitively, it seems not to make sense, because for a particular sequence, the total amount of information to generate a sequence is minus log px bits, which actually scales with n. However, if each time you are really only decoding the confident tokens, it really means that you are contributing very little amount of information, because confidence is high means the information amount is low. And if you also use the dynamic threshold, you can also show that for dynamic threshold, amount of information you generate for each round is upper bounded by this. Even if you multiply by m, the overall amount of information is upper bounded by a constant. So it naturally implies, after some simple manipulation, you'll be able to show the number of rounds needed for any confidence-based decoding is actually lower bounded by this expression, where the numerator is total amount of information you need to decode a particular sequence, and the denominator effectively is the number of bits that can be reviewed per each decoding round. Then this one, of course, it also depends on f. Say you take f to be roughly half, then it's essentially proportional to minus log px, which is proportional to n. It really means that the confidence-based decoding is not able to help you significantly reduce the number of rounds. Then, as a theorist, the second thing we figured out is to come up with intuitions to break the fundamental limits that the confidence-based decoding actually needs to satisfy. So here's an interesting example. Say that I would like to help decode the student profile. Then the student profile has certain characteristics, name, age, school, and hobby. Suppose you first follow the confidence-based approach. Then you figure out which one is more confident. Maybe for some students in a certain demography, you would like to decode the age first, maybe 18 to 22, college students. Given age, you want to decode the school, then decode hobby. Finally, you are able to decode the name. It requires 4 rounds, and generally, it's somehow the price you need to pay if you follow confidence-based decoding. And the better strategy is actually to decode the name first. The name is actually very uncertain. When you actually look at these 4 entries, this one has the highest entropy because there are so many students with different names. But once you're able to decode a particular name, you'll be immediately decoding all the other entries in parallel. So overall, the number of rounds will be significantly reduced. So the whole intuition is that you want to really focus on low confidence, high entropy tokens that's able to help you unlock so many other tokens in order to overall increase the sampling efficiency. So the solution we propose is so-called explore then exploit framework. The whole idea is that you would like to first explore high entropy tokens. You look ahead to find which one can help you unlock the number of other tokens. Then you decode it. Then you try to continue. So the whole point is to strategically explore a high entropy position that can unlock many other dependencies. Question?
Just because your example doesn't seem like you're unlocking any new information. Everything is, once you have the name, everything else is completely fixed, doesn't add any new information to the to the entropy, basically.
Yes. So the point is the following. So since the name has very high entropy, by selecting this one, I have already reviewed so much information.
Right.
There's a total amount of information all out there, but this one provides so much. Once it's decoded, I already covered everything. So that helps me reduce the total number of rounds.
Right. Basically, but you just in this case, all the information is in one round.
Yes. Yes.
But I don't quite see the unlocking part here.
Maybe later I also have the real example for you. But another good example I think I will talk about is actually code generation. Because when you think about generating a very long code, then suppose there will be some variable names. Variable names could be arbitrary, but once I just fix a particular variable name, and all the variable names referred to all these in this code base would actually be determined immediately. So that's what we call high entropy tokens. They are very uncertain, but once you decode them, they can help make many other things certain. So that's the intuition. maybe this one is also important expression. So how do we decide which high entropy tokens to decode? So it is the core insight behind this. Of course, algorithm is slightly more complicated. So a scoring function is really a multiplication of two things. One thing is the sampling quality, which refers to how confident you are about this particular token. The second thing is actually also about how many tokens are you able to produce with high confidence once I decode this particular token. Right? When you look at this, its original token, this is xj, and suppose I decode this to a particular location at j to be xj, then I would like to look at all the other potential xi's. Then I just check whether that xi passes the confidence threshold. So if this score is very large, it means that once I'm able to decode this particular low token xj, I'm suddenly able to unlock so many tokens with high confidence. So overall, my quality becomes higher. So, please.
Is it important that you also train these models with the same strategy that you use for decoding, or you just like train them to generate all the conditionals like independent of your policy in the generation?
This is such a great point. So currently, for the experiments I've been showing you, the models were not really trained to follow this decoding strategy. The models were trained to follow the original loss function I showed you, which basically predicts arbitrary locations tokens based on the information revealed to you from other arbitrary locations.
Uniformly random.
The uniformly random has been lots of work in the community showing that that's actually not the right way of training the models, because that's actually not aligned with how you decode tokens from these models. That's actually, I think, the direction lots of people are pursuing these days. So here is a slide showing that the benefit of unlocking future tokens. The blue ones will be the tokens we explored. You see that the patterns they decode becomes different. So maybe there'll be new tokens generated in the future. So suddenly, for example, here, then it helps unlock many other tokens. Okay. So here will be the experimental result on GSM 8K, which is actually a benchmark. Everybody tests on diffusion language models. So we are checking the same plot where we have accuracy versus average steps. We're using exploration batch size 1, which means that each time when we are trying to figure out what tokens will be the high entropy token, we just fix one and try to explore that. Ideally, you can actually also simultaneously explore many other tokens and see whether they are actually able to unlock many tokens in parallel. That actually is what we will show you for next slide. So for this one, you already see that once you add this exploration phase, then we get a significant improvement in terms of this Pareto frontier. We're able to improve the accuracy for given any particular number of steps. It really means that we're able to unlock many more tokens, given that we decoded the high entropy tokens first.
What is the baseline?
So the baseline is the vanilla confidence-based decoding, where you basically only look at the confidence. We should suffer from the information-theoretic lower bound. So it will be the, okay, so I will just summarize since we're running out of time. So we exactly mentioned these points. So this approach is an inference-only approach. Basically, it's a drop-in replacement for any decoding strategy you train for diffusion language models. However, it's very clear that it will be beneficial to align the training strategy with the decoding strategy. So there will be lots of things people are exploring these days, in particular reinforced learning-based approach, to try to really match the downstream gains with a particular decoding and training strategy. Ideally, it's supposed to significantly enhance the overall quality, even at the same time, also significantly improve the efficiency. Thank you.
Fascinating talk. Unfortunately, we're probably out of time for questions. We'll take them for dinner, move to the next talk. Yeah, so next we have Jack Ma from Perplexity AI on collaborative learning for open world agents.
Sounds good. You can close that window. Is there the clicker's right on your right there. Hey everybody, I'm Jack, and I'm a member of technical staff at Perplexity AI. I mainly focus on agents like the browser agent behind our Comet browser. I think this is the last talk of the evening, so I know you guys are all hungry, so I'll try to make this sort of short. And yeah, so today I want to talk about how we at Perplexity are thinking about basically like building browser agents which operate on unbounded open world environments. So I think the key thing to note here, just a brief preface of how we got here in the first place, all of this is made possible by the fact that LLMs are becoming more agentic. And basically what this means is that LLMs have always been thought of as a way of just single shot, like plain text generation. But now we've seen LLMs being increasingly trained to be agentic and basically execute multiple steps at a time to achieve some specific goal. And this has unlocked a lot of really cool use cases, one of them being a browser environment. And browsers are a really unique place to deploy such agentic AI systems because it is basically the single most important tool of any knowledge worker. And there are a lot of tasks on a browser which can be automated. And this is basically where a browser agent gets pretty powerful. And this is why this is important. So the two main dimensions that we at Perplexity are focusing on for this problem is learning across domains and learning across users. And these two sectors for building generalizable browser agents are based upon the two defining principles of any browser, right? Like any browser, you have websites and you also have your users. So I want to focus on the first part first, learning across domains. And I think the overarching question here is basically how we generalize agent performance across a seemingly unbounded number of domains. Because the World Wide Web has a bunch of websites. Let me see. Yeah, so there are basically two different approaches in which we are thinking about this problem and also other big AI labs. The first one is relying on the fact that, or the pretty good assumption that LLMs are good generalizers. And basically what that means is that LLMs have a bunch of latent knowledge about the world already. So in order to teach it how to operate within a specific environment, all you have to do is teach it on a very select number of domains and hope that it'll just scale well to all other domains. So it's basically relying on this horizontally scaling principle of LLMs. And this actually works pretty well out of the box. I want to highlight a case study by Anthropic where they trained a computer use agent. And how they trained their computer use agent is they basically took two apps. One is a calculator app, and the other is a simple text editor app. And basically what they did is they just did reinforcement learning for the model on these two apps, and it basically generalized very well to every other domain. This is very surprising because these two apps are very basic and they don't really embody the complexity of websites in a browser. And if you think about what these two apps cover, calculator app is probably the LM uses a tool to click on buttons for the calculator, and then maybe a text editor you'd have a you'd have a form fill tool or also clicking maybe key presses. So the tools are also very sparse and they barely cover the full tool set of the LLM. So we're sort of banking on assumption here that LLMs themselves are able to generalize across domains. And there's actually a pretty good strategy as evidenced by Anthropic's computer use agent. And the beauty of this approach is that it's also fairly simple compared to other approaches because you get to control your own environment. It's not like production data where a user's browser environment is very, it's very stochastic. It can differ between users, and websites are a lot more complicated. So the second aspect in which we can generalize well across domains is generalizable agent architectures. And basically the idea here is how to tune your agent architecture itself to be more generalizable across different websites and different domains. And to understand this, I think we can take a step back and look at how we as users use our browser. And at a very base level, users interact with browsers through very like low-level functions, right? Like we click, we like maybe type, we scroll, we paste some content. And although this is probably the most intuitive interface for us humans, and it's probably also a good proxy for LLMs, it's almost certainly not the best interface for LLMs themselves to work with. And at Perplexity, we've gone through countless iterations of the tools in which we actually give the LLM. And we've discovered a lot of patterns in websites where like the LLM likes to do stuff, at some actions together. For example, you can have one thing we noticed at Perplexity is the LLM likes to, for form filling, the LLM basically it has to click on an input box and then it has to paste some text. And because form filling is such a common thing across all websites, we can actually consolidate that into a single tool to do that. And this is good because it saves on latency in the sense that the LLM doesn't have to execute 2 actions at once. And it's also good because the LLM itself, it just understands its browser environment better. So yeah, the second thing is the interface in which an LLM can view a website itself. This is also very important. So there are 2 main ways in which LLMs can basically see the browser. It's one of them is HTML. If we just pass the, oops, how do I go back? Okay, if we pass the HTML to the browser agent, this has pros and cons. The pros that the LLM can see the entire website, but obviously a con is that such content is can be very bulky at times. Think about like a really long Wikipedia article, for example, and this dilutes the LLM's context. A second pretty common way in which you can view LLMs is in which LLMs can view browser environments is through screenshots. So basically, you just take a screenshot of the current viewport, and this has a couple of good things about it. First is it's usually less bulky than HTML, and because LLMs are already pretty good at like vision-based tasks, it can generalize well there. But then again, it has its own cons because by nature of a screenshot, you only see the current viewport. So you might have to scroll to see more content, or you might have like dynamically loaded content, which is not necessarily visible. So now I want to move on to the second dimension of generalizable browser agents, which is learning across users. And I think the big question here is basically like how do we improve browser agents through the countless user interactions which occur day to day on a browser like Comet. And at Perplexity, one way in which we've been improving our browser agent through user data is by doing something called site-specific instructions. And basically, at its core, site-specific instructions is priming an LLM with some with like information about a particular site that it might not have up front, so that it can execute on that information better. And we're priming the LLM at runtime. So basically, it's like injecting some tokens into the LLM. So the main flow is that you have a user, you have a lot of users actually. They have bad experiences, and then the first step is like to classify why they had a bad experience, right? So this can be due to many reasons. One reason could even be that the browser environment just breaks. For example, like maybe the LM generated the correct tool, the correct action to do, but the browser environment just didn't register it. The bad experience that we are focused on here is basically bad experiences which are due to the LLM not having sufficient knowledge about a particular website. Like one thing we saw at Perplexity is LinkedIn search. Sometimes it doesn't know how to like filter, apply filtering in LinkedIn search. So once we determine, once we filter those bad experiences, we can pass this through a very like hand-waving notion called a prompt improver. And the prompt improver's whole job is basically to take these bad experiences and convert those into targeted revisions for our site-specific instructions. And the key thing to note here is that the prompt improver can literally be anything from a human to another LLM. Like it can be as manual or as automated as you want. And at Perplexity, during the early days of building Comet, we were pretty manual, but we're also trying to make data flywheels. If you can imagine where, if the prompt improver is fully automated, it's an LLM which does this, then you could just get production data, you could pass it through a prompt improver, it'll improve the slice of instructions, and it's basically a loop. So yeah, I think I'm running out of time, but just a couple of really quick takeaways. I think all of what I've been talking about basically just highlights the fact that browser environments are very hard, just by virtue of like browser environments being stochastic, and they're also very highly personalized. Like no two users have the same browser environment, and I think this also brings up a lot of really cool technical challenges for us as well, though. And I think at the end of the day, it's going to be like a combination of like all the things we've talked about to build a generalizable browser agent. And it's working across all levels of the stack, from like model train to like their model architecture itself, and really thinking like holistically across users and domains that are gonna that we're gonna achieve the most alpha on.
Thank you very much. Any questions for Jack? Yeah.
A very quick question about the LLMs, generalized LLMs, becoming domain-specific experts. You refer to agentic models doing that, or are you saying that standard LLMs, like open source like yours and others, using things like RAG or fine-tuning can be the mechanics to make them domain expert in healthcare, finance, whatever?
Yeah.
I didn't understand the process of how you fine-tuning an LLM generalized.
Yeah, I think it's a combination, right? It's a combination of making sure that LLM's able to generalize across many domains, and that's like it's just good. It's just generally good in a browser environment. But obviously, each user is going to have their own unique use cases, and each domain is also going to have its own unique quirks about it. So there's also that. There's also that added complexity of like, how do we perform well on specific domains, especially like common domains where a lot of our user traffic is directed on. And that's where stuff like site-specific instructions can be helpful as well. I think equally as important is the like model architecture and like the underlying principles you use to build a browser agent. Like the tools that you select are basically half the battle there.
Great. Okay, Olga.
How do you guys handle prompt injection on domains?
Yeah, I think this is a very good question. It's basically, it's a big security problem for any agentic LLM, especially ones that have as privileged access as one on the browser. So I think by nature, because LLMs are trained to follow instructions, right? This is a pretty hard problem. But one way in like we've been mitigating this at Perplexity is we sort of have like a separate classifier in a sense that basically classifies whether at any step of like the trajectory of the LLM, whether something malicious is happening. So let's say a user's on a bad website X, right? And bad website X contains some hidden content, which the LM sees. At some point, it's going to end up within the LM's trajectory. And then we basically have like a classifier which takes as input the LM trajectory. And it's like, okay, is there any potentially malicious content here? And if there is, the classifier triggers, and then we just terminate. So no bad action happens. And obviously, this banks on the fact that our classifier is good. So that's also a consideration there.
Great, thank you very much, Ken. And thanks also to all the speakers of this session, which actually concludes the day's program. But I want to give a big shout out to all the speakers of today for a fascinating tour through so many exciting topics and applications, and really opening our eyes to what we know already, but it's good to see it all in one day like this, where math, modeling, and algorithms are really making a big difference on foundations as well as applications, even on a short time horizon. So I think it's been a fantastic day. So a couple of announcements. I guess. Yeah, let me just see. Yeah, we have some small gifts for attendees in the lobby, so please grab a goodie on the way out. If you're missing your meal ticket, I know these are tiny, and Amy is your savior. Go find her; she will give you a new one. And yeah, I think the faculty club is ready for us for a reception with drinks at 5 already, so we can just go over there. And then we will sit down for dinner at some point, probably 6 or something.
Yeah, 5:45.
5:45, okay.
But you can still have your drink.
Yeah, exactly. Okay, and thank you very much again for all of you for coming up here. Thanks again to the speakers.
Yeah, thank you.